packets, protocols, and ports. A packet is a logical container representing the flow of data. A protocol is a language and set of rules that network devices operate by, and a port is a numerical designation representing a particular protocol. Functionally, IP tables discards network packets according to chains of rules stored in the PC's memory. These chains organize the rules and determine the order in which they are binding. Some may ask, what is a packet? A packet, or a datagram, is a logical representation of a physical phenomena. It forms a unit of containment whereby data can be examined, routed, and filtered in regards to its destination, source, and content. The following diagram represents a datagram packet on a network. The following diagram represents a datagram of packet. A packet's information is organized into sections or categories known as fields. These fields hold different kinds of information, such as at layer 2, the source and destination MAC address, or at layer 3, the source and destination IP address. The time to live, the amount of time the packet will exist on the network until it's taken off the network, a header or checksum that's calculated to determine if there was an error during transit, as well as flags and fragment offset, the length. There's a payload, options. All these different types of field data are in the packet or the datagram. Now, packets don't really look like this. They're just oscillating light pulses if it's fiber, or patterns of electrons flowing through a wire that vary in amplitude and frequency and modulate. But this is how we represent it. This is how we understand it, or how we logically try to look at or understand a packet. Once again, the diagram is not a real packet, but it visually represents the flow of electrons or photons that physically transmit data on a network. To our naked eyes, we are only speaking of variations in amplitude and frequency, such as what would be visible on an oscilloscope. Not very intelligible to us, but very intelligible and useful to a computer. Data transmitted on a network is really just a flow of electrons, such as category 6 or 5e through copper wire, or photons through fiber, and RF if it's wireless. These modulate in amplitude and frequency. These modulations are governed by the limitations of the media on which these particles travel. For example, electrons attenuate, that is, they are absorbed after a period of time into the conductors that carry them. If it were, say, category 6 or 5e and those electrons were traveling down copper wire, there's a range limitation of about 100 meters, and after that they tend to attenuate or be absorbed into the medium, and you have to amplify the signal and resend it. A certain amount of the flow of particles converts to entropy or waste heat in a closed system. Other sources may interfere with transmitted data as well, such as electromagnetic interference or EMI from power lines and lights, RF from cell phones and transmitters, and damaged connections and equipment. To handle these errors, fields in each packet hold a CRC or cyclical redundancy check value that is calculated by an algorithm before they are sent. When these packets arrive at their destination, another checksum is calculated. If it matches the CRC field data from the source, the packet is good. If it doesn't, the packet is bad and is resent. This is just one of the ways the field data is used in each packet or datagram, and we can configure IP tables to make use of this. When multiple devices transmit messages on a network simultaneously, various protocols must be followed and applied to packets on that network. For instance, carrier-sensitive multiple access and collision detection governs collisions, where multiple devices transmit simultaneously on the same medium, on a cabled network. CSMA-CA, or carrier-sensitive multiple access and collision avoidance, does the same on a wireless network. At layer 3 of the Open Systems Interconnect model, routers route packets to different subnets based on their field data using either static routes or dynamic routing protocols, such as Routing Information Protocol and Open Shortest Path First. At layer 2, switches create connections between nodes and addresses and their MAC tables by configuring their application-specific integrated circuits. In this way, they can create full duplex connections between multiple MAC addresses plugged into any given switch. All of these services rely on field data transmitted with each packet. The flow of data, known as traffic, is governed by these standard protocols that bind to specific ports. Each port is represented by a number and can be filtered by opening or closing these ports to accept or reject packets whose field data match that port. This is how we configure and use IP tables, or any other firewall for that matter. There are many standard and commonly used transmission control protocol and user datagram protocol ports. Here are just a few of them. If you want a particular service to be offered by your server, you need to open the port so that the server can serve out that service to clients on the network. And this depends on whether you want to let the traffic in, incoming or input, or let it out, outcoming or output, or to forward it through a router to another subnet or network destination. Some of these ports and protocols include FTP, which would be 21 and 20, Secure Shell 22, Telnet 23, Web 80, and then Secure Web would be 443, SSL, Secure Sockets Layer, DNS 53, DHCP 67 and 68, Samba and NetBIOS 137 to 139, Active Directory 445, SMTP Mailout would be 25, POP3 110, IMAP 143, VPN 1723, Kerberos 88 when you deal with Active Directory replication, and Simple Network Management Protocol 161 and 162. In addition to this, there are other protocols such as ICMP, Internet Control Management Protocol, which would be things like diagnostics and the ping command. To configure IP tables or any other firewall, we must know the ports required for a particular service and open those ports while closing other ports that are not being used. Once again, as a typical firewall, IP tables controls the ports on a network interface whereby packets can enter, pass through, or exit. Ports can be opened or closed for each service or kind of traffic one wishes to allow. Other ports are closed for traffic one wishes to deny. Linux IP tables work with chains. Chains are groupings of rules that govern network traffic by opening and closing ports that can be applied or bound to an interface in a particular order. There are three types of built-in chains on IP tables. Input, which controls packets coming into the PC. Forward, which are packets passing through the PC, if it's configured as a router and multi-homed, that is, it has more than one network card. And output, packets leaving or going out of the PC. In addition to understanding these built-in chains and how they work, you want to familiarize yourself with the switches and options that you can pass into IP tables. Some of them are listed here. S for source address, D for destination address, P for protocol, J for action. Uppercase P to specify a default policy, uppercase D to delete a rule for a chain, uppercase R to replace a rule for a chain, uppercase F to remove all rules for a specified chain, uppercase L to list chain rules, and uppercase A to append or add a rule to the end of the chain. If you forget or are unsure about a particular option to use with IP tables, you can always pull up the man page. Now on to logistics and a more pragmatic approach. You define the rules which govern the traffic you wish to allow first in IP tables. Then you add the last rule, or catch-all as it is known, to the bottom of these rules. The catch-all blocks all other traffic that is not previously allowed. It must be at the bottom. Let's look at applying rules to the built-in input chain. In this first example, we want to allow HTTP traffic for our Apache 2 web server over port 80. So we would type or enter IP tables with the -A option to add or append a rule, input to specify the built-in chain, -J to specify the action, except instead of drop, that's the kind of action, -P to specify the port, which in this case is Transmission Control Protocol, and rather than allowing all TCP, we specify a destination port of 80, which is the standard for web traffic, and then -I, which is interface, in this case ETH0. You may have more than one, depending on how many NIC cards you may have installed on your server if it's multi-homed. Example 2. If we wanted to allow FTP traffic using the VSFTP or Very Secure File Transfer Protocol daemon over port 21, we would use the command IP tables, -A to add or append a rule, input to specify the built-in input chain, -J for the action, in this case accept and not drop, -P for the protocol. TCP or Transmission Control Protocol would be the protocol we wish to allow, the destination port 21, and specify the interface, in this case ETH0. Example 3. To allow secure shell traffic over port 22, again we would use IP tables, -A specify the built-in input chain, -J the action to accept, -P the Transmission Control Protocol, the destination port 22, and -I the interface ETH0. After applying the rules for incoming traffic you wish to allow to the input chain, you then apply a catch-all rule to block any traffic that does not match the specific traffic you allow. Example of a catch-all rule. IP tables, -A to add or append the rule, input to specify the built-in chain, -J to specify the action, in this case drop, -P the protocol, Transmission Control Protocol, -I the interface, and ETH0. Now remember, catch-all rules must be applied last, so after I applied all my other rules allowing specific traffic, I would then finally apply the last rule, my catch-all, denying or dropping all other unspecified traffic. In addition to the built-in chains present in IP tables, users can define their own chains. Also, there are many free open-source graphical tools to help you manage IP tables. You can also create your own tools, such as defining your IP tables rules in a shell script file and running the script automatically at boot.